Okay, let's look at chemical kinetics or reaction rates from a mathematical perspective. Again, we've already seen mechanisms a little bit. Let's look at rate a little more specifically here. So we can see that rate, or the rate expression, looks at a change in concentration or change in time, just like the speed or the rate of a car, miles per hour, change in distance over change in time. Kind of also looks like the slope of a line in math. Y2 over y2 minus y1 equals x2 over, you know what I mean. You know what rate is. I don't know where I'm going with that one. So we talked about this before. Disappearance, appearance, related stoichiometrically. So the rate is always equal to the tangent line, the slope of that line at a given point. So the instantaneous rate, any point along the line, since we know that rate is changing over time. And if I know the tangent line, I can find the change in concentration over change in time of that line and find the slope at any given point of a curved line. So again, we know that the rate is not constant during the whole thing. So, rate laws. The differential rate law is when we're trying to figure out is the relationship between concentration of reactants and the rate of the reaction. You can write a rate law in terms of products, but you don't have to. So, writing our rate laws. Again, pretty sure we can do this one. Each of the reactants raised to their coefficient, or some unknown number. All depends on if the reaction is single step or not, which you must be told. So again, reactants raised to some unknown power multiplied by the rate constant. The rate constant must always be experimentally determined. You cannot look it up in a chart or a book. So here's our problem. We want to figure out the rate law. We want to figure out the value of the rate constant and the overall order for this reaction. And we're going to do that through the method of initial rates. How does this work? Again, this is not single step. We are not told that, so we have to use data to actually solve the problem. So we want to figure out the exponents. What we have to do here is pick two experiments where one of the reactants, its concentration is changed by some factor, doubled, tripled, halved, something, and the other reactant is held constant. So for this one, we'll use experiments 1 and 2. That nitrogen monoxide, its concentration is doubled, chlorine is held constant, and if you look at the rate is being basically quadrupled. If you're not sure, take the bottom number, divide by the other number. So we can see that the rate quadruples, so the reaction with respect to NO is second order. Our equation we used was 2 to the x. The 2 to the x represents the concentration being doubled, and that equals 4 for this example because the rate is 4 times faster. Now, if we choose experiments 2 and 4, I guess you could choose 1 and 3 as well, we can see that NO is held constant and chlorine is doubled, and the rate of the reaction is also doubled. So our 2 to the x represents the doubling of chlorine, has to equal 2 because the rate is 2 times faster. Therefore, if 2 to the x equals 2, x must equal 1, or y for this example, and it's first order. So now here's our completed rate law. Rate equals rate constant, NO to the second power, chlorine to the first power. So now I want to solve for the rate constant. I'll choose experiment 1. You could choose any experiment that you wanted, plug the numbers in, and solve for K. So if I do that, I get my answer, and notice the units. Remember, the units of the rate constant, lowercase k, can always change depending on the order of the reaction. So you can see there at the second line, the number is easy to calculate. The units, the cubed goes away, leaving you squared, and you have liters per mole second. Overall order is just adding up the sum of the orders. So the overall order is going to be third order with respect to this reaction. Here's an example for you guys to try and solve again. Take a moment and solve it.
Daddy, I can't play Sonic.
Tyler can't play Sonic right now, so let's hold on for a moment.
Dad.
Sorry about that. So when you solve this, I'll choose experiments 1 and 2 to solve for the exponent of b. Doubling b gives me a quadrupled rate. Therefore, b's order is second order. I'll choose experiments 1 and 3 for the exponent of a. Concentration of a is doubled from 2 to 4, but rate remains constant. So 2 to the x equals 1. X has to equal 0. So my answer is going to be E. On this one, if we know the rate of disappearance of ozone, we want to figure out what is the rate of appearance of oxygen. So my rate of disappearance of ozone times the ratio of 3/2 gives you your answer. If I remember correctly, I think the answer is A. Again, another question. We can see B. So B's concentration is going from 0.1 to 0.3. Basically, it's being tripled. So the exponent of B is second order. So 3 squared. You have your answer. Okay, we saw this already. All right, there's your mathematics side of chemical kinetics. Again, thank you for watching.